Okay, so here's number two, and sorry, one of the kids' toys is spontaneously making noise at the moment. Um, you've got a train traveling at 10 meters per second on a straight horizontal track. It sees a red signal 135 meters ahead and immediately applies the brakes. The train immediately decelerates with continuous deceleration for 12 seconds, reducing its speed to 3 meters per second. The driver then releases the brakes and allows the train to travel at 3 meters per second for 15 seconds, applies the brakes again, and the train slows down, coming to rest. Now, one of the things that people found uncomfortable was the idea that it starts traveling at 10 meters per second. So they had this idea that you had to start with the graph going along at 10 and then applying the brakes. But I suppose it's just a familiarity with this type of question, is that the key point is really when things start to change. So at the point where he sees the red signal 135 meters ahead, that's really when it becomes of interest. So we start at this point here with the speed, velocity, so speed, but usually it's velocity, is 10, and he decelerates, so it's a straight line for speed time with constant acceleration down to the time when t is 12, and then his speed is 3. This is a bad graph, I know, but it gives you the idea. Then for 15 seconds more, so up to t is 27, it continues at 3 before decelerating constantly to rest at mystery time, whatever that may be. So that's the basic shape of the speed time graph. I think that's fairly okay. The distance travelled by the train from the moment when the brakes are first applied to the moment when the speed first reaches 3. This question is very badly answered, actually. You're just looking for this area here, A1. The distance travelled is the same as the area under a speed time graph, because distance is the integral of velocity with respect to time. Was trapezium, and as you all know, the area of a trapezium is half the sum of the parallel sides times the distance between them. So this parallel side, this parallel side. This length is 3, this length is 10. The average of 3 and 10 is 6.5, so that's a bit late. And times the distance between them is 12, so 6.5 times 12 is 78. The other way you could do it is to split it up into a rectangle and a triangle. This rectangle here is 3 tall and 3 by 12, and this triangle is 7 high and 12 across, which is the working I've done here, but trapezium is the quickest way. Either way, the answer is 78. And I've written that as A1 here, because we've got 3 areas. The area of this bit, the area of this bit, and the area of this bit. Why have I split them into 3 sections? Because we know that the total distance is 135. And we're going to use that information to work out how long this last bit is, because we know we've travelled 78 for this section. This section is 15 seconds at 3 meters per second, so we travel 45 here. So the remaining distance that's left from the 135 will be covered by this section. And it's a principle I apply here. So A2, I've written as 15 times 3, which is 45. A3 is 135, take away the other 2, and so this area is 12 meters. So we have a triangle which has an area of 12, i.e. the distance travelled for this section is 12, height is 3, so you can work out from that the base is 8. Half